All right, let's dive into a mystery that happens right on your screen probably every single day. We're talking about the invisible choices that make one app feel like magic and another, well, painfully slow. Let's get right into it.
You've totally felt this, right? You add, I don't know, 100 more photos to an album, or you're scrolling an endless feed, and suddenly the app just starts to crawl. It gets janky, but then other apps, they can handle thousands, even millions of items, and they just don't miss a beat. So what's the deal? What's the secret sauce that keeps some software fast, no matter how much you throw at it?
Well, here's the thing. The answer isn't some kind of digital magic. It's engineering. It all comes down to choices. Every single time a developer builds something, they have to decide how to organize the data behind the scenes. And those choices, they have massive consequences for performance. Speed is not an accident. It is absolutely by design.
So, to really get this, let's start with the big question. Why? Why does adding more data sometimes grind everything to a halt? To understand that, we need to take a quick peek into the secret toolkit developers use to predict this stuff.
Okay, so there's a fancy name for this. It's called complexity analysis. But just think of it like this. It's a way for developers to guess how an app will behave before they even write all the code. It's not about measuring the exact time in seconds or milliseconds, because that changes with every computer. No, it's all about understanding how the workload grows as the amount of data grows.
Now, if we're going to compare different ways of doing things, we need like a standardized rating system, right? We need a way to score an algorithm's efficiency so we can make the smart choice. And in the world of computer science, that rating system has a very specific and kind of famous name.
And that name is Big O notation. I know, it sounds super technical, but stick with me. The idea is actually pretty simple. Big O just gives us a label to classify how much work something takes as our data grows. It's all about the worst case scenario. It tells us when we push this thing to its limits with tons and tons of data, how bad can it get? I love this way of thinking about it. Is the code you're writing a cute little bonsai tree where the work grows super slowly and predictably? Or is it this out-of-control weed that just explodes and takes over the whole garden the moment you add a little more data? That's the exact question Big O helps us answer.
And that brings us to what I like to call the complexity ladder. Up at the very top, you've got O of 1, or constant time. This is the dream, the absolute gold standard. It means an operation takes the same amount of time whether you have 10 items or 10 million. It stays flat. Then you have O of n, linear. This is pretty good and really common. You double the data, you roughly double the time. Totally fine. But then we start moving down the ladder to O of n squared, quadratic. And this is where things start to get, well, pretty painful. You double the data and the time quadruples. And way down at the bottom, you've got exponential. That's basically a do not use sign for anything but the absolute tiniest amounts of data.
So what does this actually look like in real code?
You might be surprised how simple the difference is. On the left, we've got a single loop that just goes through our n items one time. That's our nice, predictable linear growth, On. But look at the right. We have a loop inside another loop. So for every single item, we have to go through the entire list again. That's n times n, and that's how we get that dangerous On squared quadratic growth. A tiny change in the code can lead to a massive, massive change in performance.
Okay, so with that theory in our back pocket, let's meet our first suspect. This is the most common, the most fundamental way data gets stored in just about any program you've ever used. The good old array. So what on earth is an array? Well, it's basically a list of things stored one right after the other in the computer's memory. The keywords there are ordered and contiguous. I want you to imagine a brand new street where all the houses are built in a perfect line right next to each other, each with its own address, number 1, number 2, number 3, and so on. This super rigid structure is exactly what gives arrays their one incredible superpower. And that superpower is its strength. It's got crazy fast access to any element. If you know the address or the index, the computer can just jump straight to it. That's a constant time, O1 operation. But this exact same structure is also its biggest, most annoying weakness. Think about it. What happens when you want to squeeze a new house into the middle of that perfectly lined up street? But let's just stop and appreciate how amazing O of 1 is for a second. Seriously, constant time. This is why you can tap on the 500th photo in a giant album and it shows up instantly. The program doesn't have to look at photos 1, 2, 3, all the way to 500. Nope, it just does a tiny bit of math to find the exact memory address and jumps right there. It takes the same tiny amount of time whether that album has 10 photos or 10,000. It's incredible. But here is the catch. Here is where it all falls apart. To insert a new item at the very beginning of our array, we can't just stick it there. We have to make room. And that means every single other element has to be shifted down by one position. If you have 1,000,000 items in that list, that's 1,000,000 move operations you have to do. We call this the array shuffle, and it is a classic linear O of n operation. This is exactly the kind of thing that makes an app feel sluggish and unresponsive. So that shuffling is a total performance killer. If your app needs to do a lot of that, it's going to feel slow. So if that's the problem, what's the solution? Well, engineers came up with a really clever alternative that's built on a completely different idea. Meet the linked list. Now, unlike an array, its elements, which we call nodes, can be scattered all over the computer's memory. They are not in a neat little row. So how does it keep track of the order? Well, each node doesn't just hold your data. It also holds a pointer, which is basically just the memory address of the next node in the chain. It's like a scavenger hunt. This train analogy is just perfect. You start at the engine, that's the head of the list, and you just follow the connection to the next car, and then the next, until you get to the end. This structure gives up that instant O1 access we loved in arrays, but what it gets in return is incredible flexibility. Okay, now let's replay that insertion scenario. Remember the painful array shuffle? Well, get ready for this. To add a new element to the front of a linked list, we don't move a single thing. We just do 2 tiny pointer changes. First, our new node points to what used to be the first item. Second, we tell the list that its new head is our new node. That's it. 2 quick updates. Boom, done. This is a lightning-fast O of 1 operation, and it completely solves that shuffling nightmare. So, what have we got? We have 2 totally different ways to store a list of things. Each one has a massive, game-changing advantage, and each one has a pretty significant drawback. And this brings us to the absolute core of what good software engineering is all about, choosing the right tool for the job. This table lays out the final showdown perfectly. If you need to jump to any element instantly, the array is the undisputed champion. But if you need to add or remove things from the start of the list all the time, the linked list wins hands down. And why is the linked list so slow for access? Well, remember those train cars? You can't just magically teleport to the 50th car. You have to start at the engine and walk through every single one to get there. That's a slow ON journey. So in the end, there is no single best answer. Great software isn't about using the newest, flashiest technology. It's about deeply understanding the problem you're trying to solve and then picking the right tool for that very specific job. More often than not, a slow app is just a symptom of a simple mismatch. The wrong data structure was chosen for the task at hand. So the next time you use an app, maybe you'll see it a little differently. That instant photo access, that's almost certainly a rock-solid array at work. That buttery smooth, never-ending social media feed, you might just be looking at a beautifully implemented linked list. These invisible choices that developers make every day are what separate the frustrating digital experiences from the truly delightful ones. Thanks for joining me on this deep dive.